Hello, I'm Dr. Dupre, and in this section we're going to discuss the chain rule and parametric equations. The chain rule is probably the most powerful rule for differentiation because it allows us to differentiate functions of functions. That is what we call composite functions. So in many situations where expressions get very complicated, what we realize is that we have some functions that are inside of other functions. How do we deal with that? Well, the chain rule is what allows us to deal with functions of functions when we want to differentiate. Well, let's see how this works. Theorem 3, the chain rule. If f of u is differentiable at the point u equal g of x, and g of x is differentiable at x, then the composite function f composed with g at x, which is equal to f of g of x, is differentiable at x, and the composite function f composed with g prime at x is equal to f prime at g of x multiplied by g prime of x. Notice what's happening here. We can think of the f in this situation as being the outer function and g of x as being the inner. It's been substituted in a sense into the function f. And so what this equation is saying is when you do that to differentiate the result, you differentiate the outer function, leaving what's inside alone, just substituting back into the derivative of the outer function, and then multiply by the derivative of that inner function. Now, in the Leibniz notation, if y equals f of u and u equals g of x, then we have dy dx equals dy du times du dx. That's dy over dx equals dy over du times du over dx. Now, remember, this Leibniz notation is sort of suggestive of slope. That is, for a little infinitesimal bit of change along a curve, or a little tiny bit, the dx changes by a tiny bit, resulting in a tiny dy. And so as u depends on x, a little change dx causes a little change du, and so the slope of g is du dx. Now, y being dependent on u, the slope of the graph of f would be dy over du. And so notice what this equation is saying in a certain sense is if I can think of these as actual fractions, the du's are canceling out. If I cancel those, I'm left with dy over dx, which is the left side. Here, but you have to keep in mind in this Leibniz notation, you've completely lost the notation as to where things are being evaluated. And so you have to keep in mind this is where dy du is evaluated at u equal g of x. So if you'd actually substituted u for this inner function and differentiated y with respect to u, you would arrive here at an expression involving u, and this would be an expression involving x. And then once you've done that and multiplied these two together, you would then have to replace u by g of x everywhere to get the actual expression for dy dx in terms of x. Now, it looks pretty simple here. You're just multiplying these derivatives. It's useful to think of why that might be true. For instance, suppose x is something like time, and suppose u is telling us position along, let's say it's a vertical axis, and y, let's think of y as being something like, maybe temperature. Now, suppose I said we have a bug crawling up a vertical pole, and he's crawling up at the rate of 2 feet a second. So du dx would be then 2. And suppose we know that temperature is increasing at the rate of 3 degrees per foot as you rise vertically. So in 1 second, the bug goes up 2 feet, but the temperature as you rise 2 feet goes up 3 degrees for each of those foot, so that's 6 degrees. In other words, the 3 degrees per foot times the 2 feet per second gives you 6 degrees per second increase in temperature. You see, so when one function depends on another like this, it's reasonable to multiply the derivatives to get the rate of change of the composite. Well, now let's look at a short summary of the chain rule. So in short here, for the chain rule, we're differentiating a composite function f composed with g at x, and the main thing here is our equation for the derivative says it's equal to f prime, the derivative of the outer function f, evaluated at g of x multiplied by g prime of x. That is, we differentiate the outer function, leaving what's inside alone, but then we multiply by the derivative of what's inside. In the Leibniz notation, if y is f of u and u is g of x, this takes the form dy dx, that is the derivative with respect to x, is equal to dy du, that's the f prime at g of x would be dy du, multiplied by du dx, which of course would be g prime of x. Now, when I look at it in this form, what I want you to notice is that a simple way to remember this is that the du's would cancel if I thought of these as symbols for ordinary fractions. Now, as we have it so far, the notation for the derivative dy dx is not really a fraction, it's really all one thing, and so we can't just cancel here, but you can think of that as a way to remember how the multiplication goes. If I were to do it so that these didn't cancel, I'd have the wrong formula. Well, what we notice from the equation giving the derivative of the composite function is that you differentiate the outer function, evaluating at the inner function, and then multiply by the derivative of the inner function, sort of an outside-inside rule. Let's look at that next. So here's the outside-inside rule. It sometimes helps to think about the chain rule this way. If y equals f of g of x, that's a composite function, then dy dx is f prime at g of x times g prime of x. In words, differentiate the outside function f and evaluate it at the inside function g of x left alone, then multiply by the derivative of the inside function. That is, we differentiate. Notice here in this composite, the f is the outer one, the g is the inner one. So we've differentiated the outer one, evaluating at the inner one, leaving it alone in effect, and then multiply by the derivative of what's inside. Well, now let's apply the chain rule to differentiate some functions. Here in this example, we have y equals cosine u with u equals sine of x. And let's calculate dy dx. According to the chain rule, that would be dy du multiplied by du dx, and where the derivative of y with respect to u is evaluated at u equals sine of x. Okay. Well, it's easy to calculate dy du. The derivative of cosine is negative sine. So we have negative sine of u. And then we have to multiply by the derivative du dx. Well, the derivative of sine x is cosine x. So there we have the product computed, but notice we don't have a function of x alone, we have a function of u in x, and so the last step would be to replace the u by sine x, and that's what we mean by evaluating dy du at u equals sine x. And so we end up with negative sine of x multiplied by cosine of x. And just to be perfectly clear, this multiplication of cosine of x here times this quantity means multiplied by the whole thing. It's not being multiplied by just the sine of x inside the sine of x. And so there's our derivative. And notice, in effect, we've differentiated the outer function cosine. with the inner function left alone and then multiplied by the derivative of the inner function. That is, suppose I wrote it all at once. I formed cosine of sine of x. That's the composite function we're differentiating. So to differentiate directly by the outside-inside rule, we would differentiate the outer function first. Derivative of cosine is negative sine, and then leave what's inside alone, and then multiply all of that by the derivative of what's inside, which is cosine x. Of course, as far as the negative sign is concerned, it doesn't matter whether it's inside that bracket or outside that bracket. It gives the same result. Well, let's work another example of the differentiation problem where we have to use the chain rule. Here we have y equals tangent of u, and u is the function 10x minus 5. So again, using the Leibniz notation, dy dx is dy du multiplied by du dx, where I can think to remember this formula. The du's are canceling. Well, dy du, what's the derivative of tangent? Secant squared. So that's secant squared of u, and that's to be multiplied by the derivative of u with respect to x. Well, obviously, the derivative of u with respect to x is simply 10. And so now, replacing the u by its expression in terms of x, we get secant squared of 10x minus 5, and all of that is multiplied by 10. Alternately, if I used the equations to write y as a function of x directly, it's the function y equals tangent of 10x minus 5. And so to differentiate then by the outside-inside rule, the derivative of y with respect to x is differentiate the outer function first. Derivative of tangent is secant squared. Keep what's inside left alone, and then multiply by the derivative of what's inside. The derivative of 10x minus 5 is simply 10. Now let's look at a problem where we're not explicitly given how the function is to be thought of as the composite of two functions. When you actually apply the chain rule in practice, you're going to have to begin to view various combinations and algebraic expressions as composite functions. So let's begin with a simple example. Here in this example, I have the function y equals quantity 2x plus 1, all raised to the 5th power. So one way to view this as a composite function is to think of u is equal to 2x plus 1. In that case, y is equal to u to the 5th power. In effect, what I can do when I'm looking for composite functions is look for various grouping symbols, such as parenthesis or radicals. Those generally signal where you can make a substitution. U equals an expression, and then y will simply be u done to as the parenthesis is. So in this case, the parenthesis is being raised to the 5th power, so we set u to be equal what's inside the parenthesis, and then y is u to the 5th. Now, once we've arrived at this breakdown, we can simply apply the chain rule. For instance, in the Leibniz form, dy dx is equal to dy du, which is 5u to the 4th, multiplied by du dx, which is, of course, simply 2. And so then that can be simplified to 10u to the 4th, but we have to replace u by its expression in terms of x. So we get 10 times the quantity 2x plus 1, all raised to the 4th power. Now we could alternately do this with the outside-inside rule. So in this case, 2x plus 1 raised to the 5th power. If I want to differentiate that, what I do is I look at the parenthesis. In effect, the parenthesis is signaling the outer function. I've got something raised to the 5th power, and what's inside is some possibly complicated expression involving x, but I don't worry about that. I just remember something to the 5th power, apply the power rule, and I write 5 parenthesis to the 4th. You might think of this in some sense as differentiate with respect to the parenthesis, but in any case, after I've done that, I'm going to copy down what's inside the parenthesis. It's to be left alone. And then finally, as the last step, differentiate what's inside the parenthesis. What's the derivative of 2x plus 1? Simply 2, and we're back where we were before. Notice these two things are identical. Well, let's look at another example of the chain rule for differentiation. And in this case, because of the subtleties of our notational conventions for powers of trig functions, you can sometimes easily overlook the existence of a composite function. Let's see how this happens. Here I have the function y equals sine cubed x. What I'm not seeing are any grouping symbols. There's no radicals, no parenthesis, no nothing. What you have to remember is this sine cubed x means the cube of the sine function, and that in effect is telling us that this is the same as the quantity sine of x all cubed, and so there's the parenthesis. You see, it's a convention of our notation, in effect, that allows us to eliminate the parenthesis when we write it, but it's really there. And so when I rewrite it with the parenthesis back in, we can now see how this is to be expressed as a composite function. What we would do is simply substitute u equals sine of x, and now what is y in terms of u? Y is simply u cubed. So you see, if y is in effect the cubing function is applied to u, then with u equals sine of x, putting those two together gives us y equals sine of x quantity cubed. So now to differentiate, dy dx is dy du multiplied by du dx. dy du is 3u squared. du dx is cosine x. But of course we have to remember to replace the u by what it is in terms of x so that we arrive at a function of x alone. So we end up with 3 times sine of x quantity squared times cosine of x, or finally writing with our usual convention in terms of powers of trig functions, this would be 3 sine squared x times cosine of x. In this final notation, it almost completely obscures the fact that we were dealing with a function of a function altogether, but it really was there. You can see it in this notation. What about with the outside-inside rule? Let's look up here. How do we do this? We, in effect, sort of think of differentiating with respect to the parenthesis, ignoring the fact that what's inside is something other than just an x alone. And so consequently, we would have 3 times parenthesis squared, leaving the sine x as it is, and then multiplied by the derivative of what's inside. Derivative of sine is cosine x. Now, once you get used to applying this outside-inside rule, then you won't have to go through this procedure of writing the function as y as a function of u and u as a function of x. Well, we know how to differentiate the square root function. For instance, we know how to differentiate y equals square root x. That's very easy. We can just use the power rule. But what if I see inside the radical there's something other than x? Well, now I would have to apply the chain rule. Let's look at an example. Here I have the function p equals square root of the quantity 3 minus t. So in effect, I have something inside the radical other than just the variable all by itself. And so that means I've got a situation where I want to apply the chain rule. Now, to begin, let's view the radical as a power. So this is 3 minus t to the 1/2 power. And so that means dp dt is equal to, let's just use the outside-inside rule now, differentiating the outer function, which is the 1/2 power function, by the power rule. That's 1/2 whatever is inside to the 1/2 minus 1. Well, 1/2 minus 1 is negative 1/2. And then finally, we have to remember to multiply by the derivative of what's inside the parenthesis. Well, the derivative of 3 minus t, derivative of 3 is 0, derivative of negative t is simply negative 1. And so finally then we could rearrange this. This is negative 1 divided by 2 and times the square root of 3 minus t, where we've used the fact that the negative exponent brings this down into the denominator position, and 1/2 power is the radical. Here's our negative 1 put up in the numerator. And so there's a simple way of writing the final result of differentiating the square root of 3 minus t. You might notice the derivative of say, square root x is 1 over 2 times the square root x. And if you remember that, notice we've got exactly the same thing. 1 over the square root, whatever's inside, and then if I multiply by the derivative of what's inside, that's negative 1, that's going to put a negative 1 up top instead of just a 1. Well, let's look at an example where we have to apply the chain rule where the functions inside involve trig functions. At this time, why don't you pause the video and try this problem on your own. Well, here in this case, we have the function r equals the quantity cosecant theta plus cotangent theta, all raised to the negative 1 power, and we want to compute dr d theta. So here, notice we have a function of a function. In the parenthesis, we have cosecant theta plus cotangent theta. And of course, whenever you have parenthesis, that's a tip-off that you have a function of a function. So for simplicity, I'm going to write u equals what's in the parenthesis, cosecant theta plus cotangent theta. This is going to simplify my computation when I go to use the chain rule, because the derivatives of these trig functions can get somewhat lengthy. They're not terrible, but in any case, in terms of this quantity u, notice r is just u to the negative 1 power. And of course, by the chain rule, we have dr d theta. What we're interested in is simply dr du multiplied by du d theta. So consequently, dr d theta is, what's dr du? To differentiate u to the negative 1 power, apply the power rule. We're differentiating with respect to u here for our first factor, dr du. So we have negative 1 times u raised to the negative 2 power. And then for our second factor here, du d theta, we just use our rules for differentiating the trig functions to differentiate u with respect to theta. Now recall the derivative of cosecant theta is negative cosecant theta multiplied by cotangent theta, whereas the derivative of cotangent theta is negative cosecant square theta. So notice we can simplify. The negative 1 multiplies through both terms here, changing those negative signs to positive signs. And so putting u to the negative 2 as a u square down in the denominator, our numerator has become simply cosecant theta times cotangent theta plus cosecant square theta, all divided by the u quantity squared. Well, the u is cosecant theta plus cotangent theta, so let's put that in for u. And now notice in the numerator I can factor out cosecant theta, because both of these terms have a factor of cosecant theta. When I do, what I'll have is a cosecant theta multiplying cosecant theta plus cotangent theta. That's cotangent theta plus cosecant theta, which is the same as cosecant theta plus cotangent theta. And all that's divided by the cosecant theta plus cotangent theta, all quantity squared. And notice what happens now. We can cancel this factor with one of the factors of cosecant theta plus cotangent theta in the denominator, and the whole thing simplifies to cosecant theta, all divided by the quantity cosecant theta plus cotangent theta. Quite a bit simpler than what we started with back here. Now, of course, the chain rule works in conjunction with all the other differentiation rules, so sometimes when we're differentiating, we have to apply all of them simultaneously. Let's look at an example that's a little more complicated where we have to apply all the rules. Here I have the function q equals sine of the quantity t over the square root t plus 1. Notice what I have, obviously a function of a function, but the function inside is a quotient. So when I go to differentiating what's inside, I'll be applying the quotient rule. But not only that, when I go to differentiate the denominator in applying the quotient rule, it itself in the denominator is a function of a function, so I'll be applying the chain rule there. Okay, so let's begin. We begin, according to the chain rule, by differentiating the outer function first. So we look at the outermost function, that's sine, its derivative is cosine, and we just copy down what's inside. And now what we have to do is differentiate, multiply by the derivative of what's inside. To do that, we apply the quotient rule. Well, the derivative of the numerator is 1 times the denominator minus the numerator times the derivative of the denominator. Well, the denominator is the square root function with t plus 1 inside, and so that would be 1 over twice the square root. Copy down what's inside, but now I have to multiply by the derivative of what's inside that radical. Well, of course, the derivative of t plus 1 with respect to t is just a 1. So in effect, I have another factor of 1. And then we divide by the square of the denominator. Well, the square of the square root of t plus 1 is just t plus 1 itself. And so consequently, what I have, well, it looks pretty complicated, but we get it done by using the chain rule together with the quotient rule. Of course, we could simplify this a little bit. Notice if I multiply top and bottom in this fraction by the radical, it'll get rid of the radical in this first term, and it'll get rid of the radical there. So, in effect, multiply the top by square root t plus 1. Square root t plus 1 times square root t plus 1 is just a t plus 1. And then square root t plus 1 by 1 over square root t plus 1 is just 1. And so this second term becomes just negative t over 2. So this could become cosine of t over square root t plus 1 times the quantity t plus 1 minus t divided by 2 all over t plus 1 times the square root of t plus 1. You see, it's simplified quite a bit, hasn't it? And now we could go even further. T minus t over 2 is just a t over 2. Just for short here, I can put that in and cross off that term. And we have t over 2 plus 1, all divided by the quantity t plus 1 times square root of t plus 1. And you might even go so far as to write this denominator as t plus 1 to the 3/2 power. In any case, simplifying is good to do if you have purposes for it, but simplification in general is not something you need to worry about if the problem is just to get the derivative. Well, of course, if we can differentiate a function of a function with the chain rule, then we can differentiate a function of a function of a function. In fact, we can differentiate a function of a function of a function of a function and so on ad infinitum. That's why it's called the chain rule. So let's look at this in the example of a function of a function of a function and see explicitly why we can think of it as a chaining process. Here I have the function y equals sine of cosine of the quantity 2t minus 5. So notice I have a function of a function of a function of t. And so the chain rule says to differentiate this with respect to t, we just begin by differentiating the outermost function. Well, the derivative of sine is cosine. And now leave what's inside alone, but now multiply by the derivative of what's inside. Well, what's the derivative of what's inside? Notice that itself is a composite function, so we look at what's on the outside of what's inside. The derivative of cosine is negative sine. So we have the negative sine function to be evaluated at 2t minus 5. And then what do we do last? Multiply by the derivative of what was inside that, which is simply a 2. So you see the derivative of the outermost function, and then the derivative of the next inner function, and then finally the derivative of the innermost function. So it's sort of a chain, you see, and that's why it's called the chain rule. Well, the methods of calculus for finding derivatives are meant to solve the problem of finding tangent lines to curves. But as far as functions are concerned, they're special curves. Not any curve in the plane is the graph of a function. So how would we deal with the situation of a curve which is not possibly the graph of a function? Well, what we do is parametrize the curve, and let's see what we mean by that. Here in this picture, I've got a curve in the plane. Here I've put the coordinate system x, y as usual, but notice it's just not possible to represent this curve as the graph of a function. It fails both the vertical line test and the horizontal line test, meaning not only is y not a function of x on this curve, but x is not a function of y. To solve this problem, what we do is think in a simple-minded term. Imagine I pick a starting point on this curve, one endpoint, and let's imagine moving along this curve in time. So as I move, I go along the curve, and it becomes the path of a motion. So instead of looking exactly at the geometric curve, I'm now thinking of a path of a motion. Notice at each distinct time, I'm at only one place on the curve. So now my location on the curve does become a well-defined function of time. And in general, if I use t to denote time, then we can think of x as being some function of time. That's the x-coordinate of my position at time t. And likewise, the y-coordinate of my position at time t is a function of t. That is, x is f of t and y is g of t as the time ranges over some interval from a to b. When t is a, we can think of being at the start, and when t is b, I'm at the end. So if here I'm starting, then in terms of this parametrization, we're moving along here. Now in that case, once we've determined the functions f of t and g of t and the interval a to b over which the parameter varies, we say we've parametrized the curve. Now it's useful to think of that in many situations as being a motion, but that doesn't mean we have to think of it that way, and the parameter could be arbitrary in some sense. There's a lot of latitude here. Just think in terms of motion. I can start along this curve and move slowly, then speed up, and then slow down, and then speed up, and then slow down, and speed up, and slow down. There's a lot of ways to go along that curve at different rates over different parts. And every way I do that leads to a different parametrization. but any parameterization, and once I've found it, will be something that I can use to calculate. Okay, so once we have a curve parametrized, then x and y are both functions of the parameter t, and so now we can ask how we find the slope of the tangent line to the curve. That would be dy dx in terms of dx dt and dy dt. Well, let's look. Parametric formula for dy dx says if all three derivatives exist and dx dt is not equal to 0, then dy dx is equal to dy dt divided by dx dt. Notice that you can think of this as fractions, a compound fraction, you might say. That's a fraction where the numerator is a fraction and the denominator is a fraction. And if I do think of it as actual fractions, the dt's would cancel, leaving dy over dx. So when you write it in this form so that the dt's cancel, it'll enable you to realize that what you end up with is dy dx, and in that way you'll always get the derivatives correct in your formula. Well, now let's use our parametric formula for dy over dx to actually calculate the equation of the tangent line to a curve when that curve is given to us with parametric equations. Here I have the curve that's given to us as x equal cosine t, comma, y equal 1 plus sine t, and I'm interested in finding the equation of the tangent line to this curve at the point where t equals pi over 2. Well, what point would that be? If I put t equals pi over 2 into the expression for x, cosine of pi over 2 we know is 0. So the x coordinate is 0. And what do I get when I put t equals pi over 2 into the expression for y? 1 plus sine pi over 2, and sine pi over 2 is 1, so we have 1 plus 1 is 2. So y equals 2 when t equals pi over 2. So what we're talking about here is the equation of the tangent line to the curve with this parametric equations at the point 0, 2. Now what we need still is the slope. We've got the point of tangency, so we need the slope of the line. That is, we need dy over dx. Our formula tells us that that's dy divided by dt over dx divided by dt. So in the numerator, we're going to put the derivative of that expression with respect to t. What is that? Well, derivative of 1 is 0. Derivative of sine t is cosine t. And that's all divided by the derivative of cosine t, which is negative sine of t. Now, we'll be evaluating this at t equals pi over 2. And so we could say at t equals pi over 2, dy dx is equal to, well, when I put t equal pi over 2, cosine of pi over 2 is 0. Sine of pi over 2 is 1, so we end up with 0 over negative 1, which is simply 0. That is, the slope of our tangent line is 0, and so consequently the equation of our tangent line is y equals 0 times the quantity x minus 0 plus 2, which we see is simply y equals 2. As an equation for the line in the plane, y equals 2, of course, is the horizontal line, slope 0, going right through the vertical axis at height 2. So that would be the tangent line, and of course, how this curve goes, notice as t increases, say, as t goes from 0 to pi over 2 and then to pi, what does cosine do? Cosine starts out at 1 when t is 0, and so we were starting out x here, and sine of 0 is 0, 1 plus 0 is 1. So you think if this curve started here and must have gone back there like that, and so consequently it hit that point with a horizontal tangent. Well, now you've seen some examples with the chain rule Remember, when differentiating using the chain rule, you start with the outer function. Differentiate the outer function, leaving the inner function alone, and then multiply by the derivative of what's inside. As far as dealing with curves which can't be expressed as graphs of functions, there what you need to do is parametrize the curve and then use the parametric formula for dy over dx in order to compute the slope of the tangent line.